In the previous video, we looked at Pascal's triangle and the concept of n choose r. Now we're going to take a look at binomial expansion and see how this is connected to both of those topics. Now, when we say binomial expansion, we're talking about things like this. Expand 2x plus 5 squared. And we know how to do that by foiling. But what about something like this? Expand 2x plus 5 to the power of 11. Certainly we could go through repeated foiling type processes to evaluate that, but it would be nice if we had some sort of shortcut. And we're going to see that Pascal's triangle and n choose r give us the ability to do that, give us a shortcut. So first, let's go back and look at this kind of expansion. If we had a generic expansion, a plus b to the power of 0, well, anything to the power of 0 is just equal to 1. And I'm going to write that all the way over here. You'll see why in a moment. If I change that exponent to 1, a plus b to the power of 1 is just a plus b. And I can think of that as being 1a plus 1b if I wanted to. There's an invisible 1 there as the coefficient. We know how to do this one. A plus b squared is going to be equal to a squared plus 2ab plus b squared. Recall that a plus b squared means the whole bracket squared, so I'm actually doing this, a plus b times a plus b, and then a squared, a times b times a, and b squared. That gives me this. Again, remember that I could put an invisible 1 and actually write it there so it's visible, like so. If I wanted to do a plus b cubed, now I'm doing a plus b times the answer to the previous row, a squared plus 2ab plus b squared. And if I go through that, I get a cubed plus 2a squared b plus b squared a plus a squared b plus 2ab squared plus b cubed. And if I collect all my like terms, I then get a cubed plus 3a squared b plus 3ab squared plus b cubed. And again, I could put in the 1's there to make them visible. Now, if you look at this, this should be starting to look kind of familiar. Take a look at the 1, 1, and then 1, 2, 1, 1, 3, 3, 1 pattern, and you'll notice that those are the coefficients of Pascal's triangle. There's also some patterns here in what's going on with the exponents. So let's make all of those patterns explicit. In the expansion of a plus b to the power of n, so now the exponent is a variable, the number of terms in the expansion, if we look back here, is related to the exponent. Here where that's a 0, we have 1 term in the expansion. Here where it's a 1, we have 2 terms in the expansion. When we get up to 3, there's 4 terms in the expansion. So if that's an n, the number of terms in the expansion is just 1 more than that. It's n plus 1. If we look at the powers of a, so a is the first term here, as we go from left to right in each of these, and it might be easiest to look at the last one, the power of a starts at 3, which matches that, then it becomes 2, then it becomes 1. And there's no a here, but you can think of that as being an a to the 0, because a to the 0 is 1. So the powers of a are going to decrease from n, whatever the exponent is, to 0 as you move from left to right. Again, they go from 3, which matches that 3, to 2, to 1, to 0. Conversely, the powers of b, the second term in the expansion, increase from 0 to n as you move from left to right. Going back here, we see that there's b to the power of 0, which is 1 here, b to the power of 1, b to the power of 2, and b to the power of 3. So the a's are going down in their exponents, and the b's are coming up. That means that the powers of a and b in each term actually have a constant sum. Here there's a cubed and b to the 0, so 3 plus 0 is 3. Here if we add the exponents 2 and 1, we get 3. Here if we add the exponents 1 on the a and 2 on the b, we get 3. And again, 3 on the b, and you can imagine an a to the power of 0, we get a sum of 3. And if you look back at the other rows, you'll see that as well. So in each term of the expansion, the sum of the exponents on the a and the b are summing to that exponent on the original expansion, which was n. So the powers of a and b in each term sum to n. There's a number of patterns coming that we see coming through here. The coefficients of this expansion, as we said, come from Pascal's triangle. And in row 3 of Pascal's triangle, we see this, and that corresponds to that 3 there. So the coefficients come from row n of Pascal's triangle, where n, again, is the exponent. And as we saw in the previous video, we can also think of the coefficients in Pascal's triangle as n choose r. So let's use that now to expand this binomial, 2x minus 5 to the power of 4. And we could do that by writing out 2x minus 5 times 2x minus 5 times 2x minus 5 times 2x minus 5 and going through a long foiling process with these. But now that we've seen that there's a pattern, we can use that pattern. The first thing we're going to do is write down the coefficients. And we said that in this expansion, if that's a 4, the coefficients are going to come from row 4 of Pascal's triangle. So the first coefficient is going to be row 4 entry 0. The second coefficient is going to be row 4 entry 1, then row 4 entry 2, row 4 entry 3, and finally row 4 entry 4. Then we said that if this is A and this is B, in other words, A is equal to 2x and B is equal to negative 5, the negative belongs to B as well, then each term is going to have both of those, but the powers are going to change. So let's write those all in. Let's write in 2x and negative 5 for all of these terms, and then come back and fill in the appropriate exponents. And I'm going to put a plus in between all of them right now, and we'll see that some of those signs will change. So I'm just putting in 2x and negative 5 for each of these. Now, we said that the powers on A, the exponents on the first part of each term, are going to start at 4 and go down by 1 each time. That means this one is a 4, this one will be a 3, this one's a 2, this one's a 1, and this one's a 0. Conversely, the powers on B, the negative 5 in this case, are going to start at 0 and go up by 1 each time until we get to 4. And that means that the sum on these, 4 and 0, 3 and 1, 2 and 2, 1 and 3, and 0 and 4, is always 4. Now we can go through and evaluate each term. Using either a drawing out of Pascal's triangle or using our calculator and doing all the different chooses, we can work out what 4 choose 0, 4 choose 1, 4 choose 2, etc. is. So we know that 4 choose 0 means how many ways can you choose 0 things out of 4, and there's only one way of doing that, choosing none of them. Remember that this 4 now applies to both the 2 and the x, so it's going to be 16x to the power of 4, and negative 5 to the 0 is just 1. How many ways can you choose one thing out of 4? Just 1. Sorry, 4. Excuse me, you can choose them 4 different ways. 2x to the power of 3 is 8x cubed, and negative 5 to the power of 1 is negative 5. How many ways can you choose 2 things out of 4? Either with your calculator or with Pascal's triangle, you can work out that that's 6. This becomes 4x squared, and negative 5 squared is positive 25. 4 choose 3 is 4. 2x to the power of 1 is just 2x, and negative 5 to the power of 3 is negative 125. How many ways can you choose 4 things out of 4? Only one way. 2x to the power of 0 is just 1, and negative 5 to the power of 4 is positive 625. Further evaluating, we get 16x to the power of 4. 4 times 8 times negative 5 is negative 160, so we get negative 160x cubed. 6 times 4 times 25 is 600, and then we have x squared. 4 times 2 times negative 125 is negative 1,000, with 1x plus 625. So we've been able to use the pattern that we established earlier to expand that without going through this long and kind of error-prone foiling process. In general, then, we can think about this expansion, a plus b to the power of n, and we saw that the first coefficient is going to have that n up here in the top, and the bottom is going to be a 0. If we look back here, the top is a 4, which matches that 4, the bottom is a 0. Then we saw that we had the two parts of this expansion, a and b, which we wrote out. This bottom number here matches the exponent on b. The bottom number here matches the exponent on b. So here we see the bottom number here matches the exponent on b. And then the other one has to sum with it to make n. The next term then, the top is going to be still n, but the bottom ticks up by 1. If we look back here, the top is still 4, but the bottom ticked up by 1. Once again, this number matches that number, 1 and 1. So if I put a and b here, this number is still 1, but now in order for these two to sum to n, this one has to come down by 1. If I move over 1, the top number here stays n, the bottom number becomes 2. I have a and b. The exponent on b matches the bottom number, so I fill that out first. I put a 2 up there, and then in order for these two to sum to n, this is now n minus 2. And that's going to carry on until we get to our final one, which is n on the top, choose n on the bottom. Then we have a to the power of 0 and b to the power of n. And these brackets that I have around a and b are not actually necessary, but I've put them there, so I'll leave them there. So that's the general pattern. You start from n choose 0, work up to n choose n. The number on the bottom matches the exponent on b, and then you can work out the exponent on a by making them sum to n. Now, if we wanted to number the terms in the expansion, this would be the first term, the second term, the third term, etc. Notice that the first term has a 0 in the bottom of the choose notation and a 0 as the exponent on the b. The second term has a 1 in the bottom of the choose notation and a 1 as the exponent on the b. The third term has a 2 in the bottom of the choose notation and a 2 as the exponent on the b. So this number and the exponent on the b is always 1 less than the number of the term in the expansion. Therefore, if we wanted to talk about the general term of the binomial expansion a plus b to the power of n, term r plus 1 would have an n choose r in it. If we wanted the 13th term, this number of the bottom would be a 12. If we wanted the 100th term, then this number on the bottom would be a 99, because the first one starts at 0. Then we have an a and a b, and we said that the exponent on b always matches that, so it would be r, and then the exponent on a would be n minus r, because these two always have to sum to n, the top number in the choose notation. Again, if we go back here, you can see for the third term, this is a 2, that is a 2. Therefore, this one has to be an n minus 2 so that they both add to n. And this is the third term. Therefore, this is a 2. So this then is the general term for the binomial expansion, and we're going to use this to solve problems in just a moment. So here's the first problem. Find the coefficient of x to the power of 6 in the expansion of 2x minus 3 all to the power of 9. Now clearly we don't want to expand this whole thing by foiling, because there's going to be 10 terms in this, and that's going to be long and tedious, and it's also going to be error prone. So we need a shortcut, and the patterns that we've just been looking at are going to give us that shortcut. So we know from what we just looked at that the general term, in other words, any term of the expansion, is going to look like that. So term r plus 1 is going to be of the form n choose r, a to the power of n minus r, b to the power of r. Any term in the expansion is going to look like that, and we just need to figure out which one is going to have an x to the power of 6 in it and work out its coefficient. Now I have some unknowns. Remember, this is of the form a plus b to the power of n, and I can fill in what some of those unknowns are. So n is equal to 9, a is equal to 2x, and b is equal to negative 3. I don't know what r is, because as we saw before, r, the number on the bottom, increases by 1 each time, and I don't know which term is going to have the x to the power of 6 in it just yet. So let's fill in what we know. Term r plus 1 is equal to n is 9, so 9 choose r, times a is 2x, and that's to the power of 9 minus r, because n is 9, times negative 3, and I'm putting the negative 3 in the bracket so I make sure the exponent applies to it, and r we don't know. So I have term r plus 1 is equal to this. Now I'm going to rearrange things to separate out the x from the numbers and bring all the numbers to the left-hand side. So I get term r plus 1 is equal to 9 choose r. This 9 minus r in the exponent applies to both the 2, so I'm going to write it like that, and the x, which I'm going to separate out like that. And then I have negative 3 to the power of r. Now let's move the x this way and all the numbers this way. Term r plus 1 is equal to 9 choose r, 2 to the power of 9 minus r, negative 3 to the power of r, and x to the power of 9 minus r. Now, in order for this thing to have an x to the power of 6 in it, 9 minus r has to be equal to x, so that this is a 6. So for x to the 6, 9 minus r has to be equal to 6, so r is equal to 3. Now I can go back in and sub in r is equal to 3. If I do that, I get term 4 is equal to 9 choose 3. 2 to the power of 9 minus 3 is 6. Negative 3 to the power of 3. And x to the power of 6. 9 choose 3 is 84. 2 to the power of 6 is 64. Negative 3 to the power of 3 is negative 27. And then I have x to the 6. Multiplying all of those together, I get negative 145,152 x to the power of 6. So this part here is the answer to the question, because that is the coefficient of x to the power of 6. So the process we used was we wrote out the general term, the formula that any term in the expansion will have to fit. We filled in what we knew, which was n, a, and b, and then we simplified, bringing all the numbers to the left-hand side, the x to the right-hand side, and we knew that that exponent had to be equal to 6. We worked it out and then plugged it back in. Let's look at another example of the same kind. Here we're asked to find the term independent of x, in other words, the constant term in this expansion. That means when we expand this, we can expect that there's going to be one term with no x in it at all. And if you think about it, that makes sense, because here we have x squared and here we have 1 over x. As the expansion progresses, the powers of this are going to go down and the powers of this are going to go up, and there looks like there might be a point where they balance out and cancel. The key to this kind of question is to approach it the same as we did the one before, but think of the term independent of x as being the one with an x to the power of 0 in it, because x to the power of 0 is equal to 1. So now we can approach this question in the same way we did the last one. We know that any term in the expansion is equal to n choose r times a to the power of n minus r, b to the r, and that's going to be the r plus 1th term. And we know that in this case, n is equal to 12, a is equal to x squared, b is equal to 1 over x, which we can also write as x to the power of negative 1, and r is what we don't know. So if we fill those in, term r plus 1 is equal to 12 choose r, x squared to the power of 12 minus r, and x to the negative 1 to the power of r. That becomes 12 choose r, x to the, using our power of a power rule, we multiply our exponents together for both of these. So we have 2 times 12 minus r as this exponent and negative r as this exponent. If we multiply that out, we get x to the power of 24 minus 2r times x to the power of negative r, and combining those we get 12 choose r, x to the power of 24 minus 3r. Now, for the constant term, we have x is equal to 0. So for x is to be equal to, for x to the power of 0 to be what we have here, 24 minus 3r has to be equal to 0. Solving that by bringing the 3r to the other side and dividing by 3 gives us r is equal to 8. So now we can sub in r is equal to 8, and we get that term 9, 8 plus 1, is equal to 12 choose 8 times x to the power of 0. And using our calculator, 12 choose 8 ends up being 495. And x to the power of 0 is 1. So the term independent of x, the constant term in this expansion, is going to be 495. So that's binomial expansion.